introduce our next speaker, who is Franz Skarman, who's going to be talking about an overview of the embedded Rust ecosystem. All right, Franz, do you want to say hi real quick to make sure your mic's going?
Hi, is it working?
Perfect. Sounds great. So we're going to hand it over to you, and we'll see you all at the next break.
All right. Thank you. So like James said, I'm going to give you an overview of the embedded Rust ecosystem. And the reason I want to do this is because there are a whole lot of crates out there, and what they do and their connection to each other may not always be clear. We've already seen a couple of crates today, like drivers and RTIC, and we'll probably see many more. So hopefully this talk will sort of show you how everything is connected together. My name is Franz Skarman. Online I go by the Zoc2. I talk too much about Rust sometimes, to the point where even non-programmers are talking to me about Rust, which is kind of strange to happen. In the embedded world, I am a maintainer of the STM32F1XX HAL crate, which I hope that the name of that crate will make more sense after this talk than it does now, if it doesn't make sense already. And fun fact, my desk is covered in Rust. My keyboard, I hope you can see that, runs Rust, and a couple of other projects I have also run Rust, which is kind of fun. That's not very important, though. It's more important who you are. I presume quite a lot of you are here as embedded Rust users already, and then most of the content in this talk probably won't be new, but feel free to stick around anyways. For the people who are interested in this talk, I would assume that you come from one of three categories. You may come from an Arduino background where you've done embedded programming at a higher level, like Arduino or maybe Raspberry Pis, but you haven't gone down to the lowest level of microcontroller programming. You may be coming from an embedded C background, and are used to working at that lower level. Or you may just be a Rust user who is interested in embedded development, and I hope that this talk will be interesting to all three of you of these categories. So like I said, the goal here is that I want to explain to you why there are so many crates and what they do. And I think the best way of doing that is by showing you the need for them, sort of showing you how you can work up your way up to an ecosystem that looks the way it does today, starting from nothing. And what that means in practice is that the initial code is really not something you would write in Rust, so don't be scared when there's a bunch of weird code on the slides. It's more important to look at the sort of structure in the code and the general operations that I do. With that said, let's dive into this lowest level. How do you program a microcontroller? And generally, you do that by controlling registers, or writing and reading from registers in order to affect the outside world through the microcontroller's pins. The registers are typically memory mapped, and what that means is that you write to them by writing to a specific address in memory, and that write gets intercepted at some point and handed off to the peripheral, which controls the pins. And to see what to write where and when to write it, you should read the datasheets for instructions. I think this will all be more clear if we give you an example. So the example I'm going to show you is sort of the hello world of the embedded world. Turning on an LED. I'll use an STM32F1 processor because it's the one I'm most familiar with, but the process is similar for almost all microcontrollers out there. So the first step is to read the 1000-page datasheet of the processor. And you don't need to read all the 1000 pages to turn on an LED, but to turn on the microcontroller and start up the corresponding parts and turning on the LED, you probably need about 100 pages of reading. The process, once you've done that reading, is that you start with powering up the GPIO peripheral, that stands for General Purpose Input-Output, and is for just turning pins on and off or reading from pins directly. You turn it on in a peripheral called RCC. Then, once you've done that, you want to configure the pin you are interested in as an output, and you need to set that output in the correct mode, because there are many modes that can create outputs in different ways, in different electrical ways, and you need to set one that is suitable for your task. And then finally, after all of this, you can set your pin to high, and your LED will hopefully turn on. So, reading a bit more in the datasheet, let's say we want to turn on pin 13, and we want to set it as an output. You will find a table like this. Now, I'm not expecting you to see all of the details in this table. It's more of the general structure, but it gives you some information. We have a control register for the pin, or for the pins in a bank, a GPIO bank, and that's offset by 4 from the start of that GPIO peripheral. So we have an address to the peripheral, and then we want to offset that to get the control register. Then we want to write some values to that register. And from this, we can see that we want to write a 1-0 in bits 20 and 21, and a 0-1 in bits 22 and 23. And this is for setting the mode, the output or the input, and the configuration, the type of electrical output we want. And the same is true for the output value. We have a specific bit we need to change in a specific register. In Rust, that would look something like this. I said before we need to start the GPIO functionality in the RCC peripheral. That's done in the startup GPIO function because it doesn't fit on the slide here. Then we compute some addresses. So we have the start of the GPIO bank, and then we have the control register offset and the offset for the output data register. So these will get added to the start value. The patterns we want to write to specific places are 0-1 for the output mode and 1-0 for the push-pull mode. And then we can actually do this writing. So we compute the address using normal arithmetic, and then we dereference that as a pointer, as a U32 pointer, because it's a 32-bit processor. And then we compute the value we want to write. So we wanted to write 0-1 to bits 20 and 21, so we have to shift that 20 bits to the right, or to the left, sorry. And the same thing is true for the push-pull configuration, shifted a bit more because that's where the configuration is stored. And we do a bitwise OR between them. And then the same thing is true for output. So we compute the address of the output data register and set the 13th bit to a 1 to actually turn on an LED. Right, that was not very fun. At least I don't think that's fun code to write. It's very unsafe. It's really unergonomic. We're throwing a bunch of magical constants around with dereferencing pointers, which you almost never do in Rust. Yeah, we really don't want to work like this. Luckily, the manufacturers of microcontrollers often publish SVD files, which describe the function of each register in a way that the computer is better at understanding. So in the SVD case, that's XML. And then there's a tool called SVD to Rust that generates crates from these SVD files. So by applying a few patches to kind of make the SVD files a bit nicer to work with and fix some errors that are often present in the SVD files, and then running the files through SVD to Rust, we get what's called a Peripheral Access Crate, a PAC. It's a mostly safe interface around all of this register manipulation, and that interface is created using a whole lot of zero-cost abstraction. And this is similar to what was talked about in the Writing a Good Driver talk that was earlier today. And as a bonus, we also prevent reuse of peripherals. Once we have this SVD file, or as PAC, we have a struct representing each register, and we only have one of that for each register. So if we want to share it for some reason, the ownership system will make sure that we do that properly. In code, the same thing we did before, turning on the LED, looks like this instead. We again start the GPIO function in the RCC register, and then the code for setting the mode and the configuration of pin 13 is much nicer. We want to modify the CRH register of GPIO-C, setting the mode of a pin 13 to an output, and the configuration of pin 13 as a push-pull. And that's all we have to do. Now the pin is configured. Then we want to actually change the output. And to do that, we want to modify the output data register, setting the output data of pin 13 to high. All right, this was a much nicer interface, I'd say, and I hope you agree. It does this through a lot of zero-cost abstractions. So you can see there's a bunch of closures going on here, and there's a bunch of weird function calls. All of this gets optimized away by the compiler, though it's only done in release mode. So if you run your embedded project in debug mode, it may be much, much slower than it is in release mode, which is a pitfall that is easy to fall into. But luckily, the fix is to just compile with release mode, and your code will be blazingly fast. We fixed most of the unsafety now as well. There's no unsafe in this code example, but there is some unsafe in some cases when working with PACs. Unfortunately, there are still some issues. The key one is that there's no check for dependencies between peripherals. Earlier, I said that you need to start the GPIO function before you can configure the registers. That's done through that start GPIO function, but there's never any check that we run that. If we don't, the program will misbehave, and we'll only find out at runtime after a whole lot of debugging. The same thing is true when we talk about initialization. So there's no check for that you set correct values in every register. You may have combinations that are impossible or that don't do the thing you expect. So the bottom line here is that we still need to read these 100 pages in the datasheet to effectively work with a microcontroller. Not very fun. The fix for that in Rustland is to use hardware abstraction layers, or HALS. There are higher level interface around this register manipulation. And if you're used to embedded C, you may also be used to HALS. But I would say in general, the HALS are much higher level than they are in embedded C, closer to Arduino code than to embedded C HALS. So yeah, how would turning on an LED in a HAL look like then? Well, we first need to start up the GPIO or the RCC register, put it in a known state that the HAL can work with. That's done through the constrain function or something similar. And that gives us a struct for the RCC register that we can then pass to the next function, the function that configures the GPIO pins themselves for the GPIO peripheral. In the STM32 HAL, or F1 HAL, that's called split because it does a bunch of other things than just turning on the LED or turning on the GPIO peripheral. But the key thing here is that we have to pass this RCC register to the split function. And if we don't have access to that RCC register, that means we haven't started up the RCC peripheral, and that means our code would misbehave at runtime, but we get told that at compile time here. So once we have this GPIO-C struct, we can configure the pin we're interested in, pin 13, and we want to set it as a push-pull output. And this is a much higher level function call. There's no chance of misconfiguration, for example, setting it as a push-pull input, which doesn't make sense. So we get some safety there. And again, there's a check that we have initialized the GPIO before we start configuring it. And finally, we just do led.setHigh to turn the LED on, and hopefully it turns on. And again, we make sure that we configure the pin as an output before we can turn on the LED, because otherwise we don't have a setHigh function on this struct. So the whole way through this, we get guided by the type system to make sure we're not doing anything stupid. So we have a high-level interface, and we have type state that ensures correct initialization, meaning that we rarely have to read the datasheet when working with HALS. Right, so the next step is to work with something more advanced than just turning on an LED. Let's say we want to talk to this ultrasonic distance sensor. It has two pins, one called trig and one called echo. To use it, you send a pulse on the trig pin, and after a while you get a pulse back on the echo pin. And the length of that pulse is proportional to this distance that the sensor measured. So using our HAL, we can define a function that does a measurement from this sensor. The function takes a timer and two pins, trig and echo. At the type system level, we ensure that the pins are configured as outputs and inputs. If they're not, we'll get an error. Then we send the start pulse, using just the setHigh and setLow functions we saw before, and the wait function on the timer. Then we simply have to wait for the pins for the return pulse to arrive, and measure the duration of that pulse. To use this, we do the initial setup I showed before. I just moved that into a function here. And then we configure our pins, so we say that we need PA0 to be a push-pull output, PA1 to be an input, and the timer to be a configured timer in the HAL. And then we can just call measure distance using these pins. Every time we do output, or if we forget to use output or to configure the pin as an output or an input, again, the type system will tell us and will avoid debugging that issue at runtime. So what we just did was make our first driver. Drivers in embedded Rust is any crate that talks to external peripherals through a HAL, or it could be without a HAL as well. We use types to ensure that things are configured correctly, and we also use ownership to ensure that timers aren't shared. So to go back to the previous example, we made sure that the pin is in an output. If we didn't, unlike Arduino, where you could set pin mode or do digital write on a pin that hasn't been set to an output as using pin mode, we get that check at runtime. And also, once we've done this setup for the timer, for example, or these push-pull outputs, we've taken ownership over the pins and the timers, so we can't accidentally reuse these pins or timers somewhere else. So all of this makes sure that a lot of the debugging we have to do, we may have to do in hardware, is done at compile time here. All right, so after a while, someone else makes another HAL for another microcontroller. It's likely that this HAL does similar things. All the microcontrollers will probably have GPIO functions. All of them will have timers and so on. But it's also likely that it has slightly different APIs, because the registers aren't the same in every microcontroller, and the preferences of the developers may be different. So we may have focused a lot on type safety. They might defer a bit of the type safety on runtime to make initial development easier. But the bottom line is that we have two projects that do similar things with different APIs. Unfortunately, our driver that we wrote for that sensor uses our types, and that driver will not be compatible with the other HAL. So they will have to write their own measure distance function for that ultrasonic distance sensor, and if they develop a driver, we won't be able to take advantage. So we're duplicating a lot of the work, and that's not really good. Enter Embedded HAL. Embedded HAL is a project that provides traits for common peripherals in the microcontrollers: GPIO pins, timers, serial communication, and so on. Then Embedded HAL lets HALs implement those traits, and by doing so, drivers can use the traits in the embedded HAL or in embedded HAL to implement their functionality, and by doing that, they are compatible with every HAL in the ecosystem. So we only have to write one ultrasonic distance sensor driver, and every HAL can take advantage of that work. To convert our ultrasonic distance sensor driver to use embedded HAL traits is quite simple. We imported traits from embedded HAL called input pin, output pin, and timer, because that's the three we used. Then we just make the function generic over the input pin and the output pin and the timer. I messed up here. And we just replace our concrete output pin with a generic one. And then the code can remain the same as before, because we use the same names of the functions as would be in embedded HAL. And by doing so, we enable reuse of this ultrasonic distance sensor across the ecosystem. So that's sort of the end of the stack of crates on top of register manipulations. But there are some other crates that you will come across, and that I want to explain next. The first one is RTIC, Real-Time Interrupt-Driven Concurrency, which is a framework for building real-time systems. It provides tasks and communication between the tasks and enables real-time analysis, among a whole lot of other things. If you haven't already, you should go back and watch Emil Fresk's talk about this, which he gave just an hour or so ago, because it goes into a lot more details than this. It should be noted that this crate was previously known as RTFM, or Real Time for the Masses, but that acronym turned out to be a bit weird, so they renamed it to RTIC a month or so ago, which means that you will still come across this RTFM name, but just remember that RTFM and RTIC are the same thing. You will also come across crates called board support crates, and what they do is provide utilities for breakout boards. So for example, I have this Teensy 3.6 here. It has a microcontroller in the middle, but it also has a bunch of pins on the outside, which, unlike the microcontroller, are labeled with Arduino names. So pin 1, 2, 3, and so on, instead of, for example, PA1, PB1, and so on. So what the BSP for this board would do is replace the names of those pins. It would also probably include drivers for the peripherals. So this one has a micro SD card slot up here. And the BSP for a Teensy 3.6 would include a driver for that. Unfortunately, in the Teensy case, I don't think there is a BSP for it yet, if there even is a HAL. But in general, that's what a BSP does. Finally, you will probably come across crates with the cortex-x name. Generally, in the embedded world, you would come across cortex-m, but there is also A and R. And cortex-m and similar is the core of many ARM microcontrollers. So it has some timers, it has some debuggers, it has interrupts, it does the actual instruction execution. And the Cortex-M crate itself is essentially a peripheral access crate for the core peripheral, so the timers and the debuggers and so on. There's also a crate called Cortex-M RT, which has a minimal runtime, so handling exceptions, handling entry points, handling interrupts, and so on. And if you're working with a PAC, that will be included with the RT feature. And finally, you will probably come across some crates with the postfix-semi-hosting. There's Cortex-M semi-hosting and Panic semi-hosting, and maybe a few others. And they provide conveniences for working with debuggers. So typically, in the way I worked with them, you would program your devices using this debugger like this or similar. And then Cortex-M semi-hosting allows you to print to the debugger console and a whole bunch of other things that are useful when working with the debugger. Though be careful, if you're using semi-hosting and your debugger isn't attached, your program will crash and your controller will do nothing. That's fine if you're just using it for panic messages, but if you're starting to print to the debugger and then disconnect that, things may go wrong. So keep that in mind. With that, we're getting to the end of my talk. Embedded HAL is sort of the core of the ecosystem. It's what HALs implement, or the traits in embedded HAL are implemented by HALs, and this is usually done through peripheral access crates. Then drivers can use these embedded HAL crates to talk to external devices. And that allows reuse across the ecosystem. There's also a bunch of other crates that you will come across. RTIC to provide concurrency, SVD Rust for generating PACs, the Cortex something family of crates, and so on. So if you're starting out with embedded Rust, you may still have the question, where should I start? Should I always start with HAL? Should I start with a PAC? And I would say HALs are really nice. You want to work with a HAL if you can. So if you're starting from scratch, I would say pick a microcontroller with a good HAL. What a good HAL is might be a bit difficult to tell, but pick one with a well-maintained HAL. Check when the last commit on GitHub was, how many pull requests there are, and so on. If you have a specific project in mind with specific hardware, you should start off by looking for a HAL, and I'll give you a list of HALs that exist at the end here. If there are no HALs for your hardware, check if there's a peripheral access crate. Maybe you can use that to build your own HAL. Or check if there are SVD files and use SVD to Rust to generate it. And then build your HAL on top. Now, this will be a whole lot more work, but that work will only have to be done once, and then the whole community can take advantage, especially if you're using the embedded HAL crates. And the same steps apply for drivers. You should look for a driver if there isn't one already, or to see if there isn't one already. If there isn't, you may want to build one. And if you do that using the embedded HAL crates, then everyone can take advantage, and you can take advantage of every HAL in the ecosystem. So you're not locked into one microcontroller. Finally, and this is my last slide, this is just a few resources. Almost all of the relevant resources for embedded Rust can be found on this Rust Embedded/Awesome Embedded Rust repo. That has a list of HALs, a list of drivers, a list of PACs, a list of chat rooms, tutorials, and probably a bunch of other things that I'm forgetting. There's also the embedded working group chat room, where you can come and ask questions if you run into any issues. And finally, there's the community Discord, where you can also ask questions in the embedded channel. I think both of these are linked from the Awesome Embedded Rust repo. And with that, I want to thank you for listening, and I wish you good luck with all your embedded Rust projects.
All right. Thank you very much, Franz. We did actually have a number of questions in the chat, so let's see how many we can go through in the next 5 minutes or so. The first question that I see is, what is the state of code sharing between similar HALs? So not necessarily through the embedded HAL traits, but rather between something like the STM32F1XX and the STM32F4XX.
There isn't much of that as far as I know, at least not in the STM case. There might be in other families of microcontrollers. It has been discussed recently, but I'm not aware of any effort to actually share code there. Though it would be nice because I think we're duplicating a lot of the effort.
Yeah, I know a lot of the different chips have overlapping peripherals, but a lot of similar chips have non-overlapping peripherals as well.
Yeah.
All right. The next question I have is, are the HALs just written by enthusiasts? Are there any standards over what a HAL should provide?
Yeah, they're all, as far as I know, most are written by enthusiasts. Although I'm guessing Ferris does some, for example, maybe.
I know we definitely work with the NR52 the most.
Right, yeah. But yeah, there's no vendors making official HALs yet, as far as I know. And what was the other question?
Let's see, on that one there was, are there any standards on what a HAL should provide?
All right. Well, I guess there's the embedded HAL crate, so it's useful if the HAL implements everything in embedded HAL, because otherwise you may have drivers that don't work with embedded HAL, or don't work with the HAL, but work with embedded HAL. Other than that, I don't think there are any standards, but in general, you would want to support everything that is on the microcontroller, I would say.
Definitely. So someone was asking about debug versus release. You mentioned the pack code being slow in debug mode. Someone mentioned that they've seen that you can override optimization flags in Rust for specific crates. Is it reasonable to optimize just the pack and then leave the user code debug optimized?
Yeah, I think that would make sense. I think I tried that like a year ago with some crate, but I'm not sure if I got it working. Back then, I think it was a nightly feature flag as well to override dependencies. I'm not sure if it's that case anymore.
Yeah, I think that's stabilized now. So I think you can override profiles for specific crates now.
Yeah, it would be useful to investigate because it's not very useful to jump into the pack code with the debugger anyway.
Okay. Well, I'm not seeing any more questions, so unless one comes up in the last second, I'm scrolling through to make sure I haven't missed anyone, but I think we've answered all the open questions right now. There's definitely some more conversation going on, so it'd be great to have you join the Matrix chat after this, but otherwise, Thank you very much for a wonderful talk.